Next, we're going to look at an interesting couple of properties about functions that are defined by power series. So if the function f of x equals the sum from 0 to infinity of a sub n times x minus c to the nth power, so that's a power series centered at c with a radius of convergence of r greater than 0, then on the interval from c minus r to c plus r, f is differentiable and therefore continuous. Moreover, the derivative and antiderivative of f can be found as follows. The derivative f prime can be found as basically the derivative of each term. So you would have a sub 1 plus 2a sub 2 times x minus c plus 3a sub 3 times x minus c squared, so on and so forth. And the integral can be found by integrating each term and then adding a constant c. So you can see that here. Basically what you're looking at is this already looks like the power rule for a derivative. So when you take the derivative, you just go one further. And then here we end up with what we see here. The radius of convergence of the series obtained by differentiating or integrating a power series is the same as that of the original power series. And that right there is part of the important part of this theorem. But the interval of convergence can change as a result of behavior at the endpoints. So you know that the numbers are going to be the same for your interval of convergence. You just don't know if you're going to have the same parentheses and brackets. So let's look at an example. It says find the derivative of f of x equals x to the nth divided by n factorial, and we've got 1 plus x squared over 2 plus x cubed over 3 factorial, so on and so forth. So this is a 1 factorial, or 0 factorial, a 1 factorial, and a 2 factorial in that denominator. So if I go term by term, f prime of x would be 0 plus 1 plus 2x to the first power over 2 plus 3x squared over 3 factorial plus 4x cubed over 4 factorial, so on and so forth. And you can see what's going to happen is I'm going to end up with 1 plus x. See, the 3 will cancel with the 3 here. So we'll have x squared over 2 factorial. The 4 will cancel with the 4 here, and we'll have x cubed over 3 factorial. Now, I don't know about you, but that looks a lot like the original thing that we started with. And as it turns out, this series is its own derivative, okay? So that can happen. And in fact, it can be its own integral as well, give or take a constant. Let's look at another example. It says find the intervals of convergence of f of x, f prime of x, and the integral of f of x dx for the sum from 0 to infinity of x over 3 to the nth power. I'm not actually going to find the derivative in the integral here. I'm just going to find the intervals of convergence. So the original sequence here, the original series here, f of x, this is a geometric series. You can either observe that and use it to your advantage, or you can use the ratio test. There's nothing wrong with either way on this one. R is going to be x over 3, so we want the absolute value of x over 3 to be less than 1. That tells me that x over 3 is going to be between -1 and +1, or x is going to be between -3 and +3. So r equals 3, and we just need to check the endpoints. So I will have x equals 3 would give me the sum from 0 to infinity of 3 over 3 to the nth power, which is 1 to the nth power, which gives me the sum from 0 to infinity of 1, and if you add 1 together infinitely many times, you get infinity, so this one diverges. And for x equals -3, we'll have the sum from 0 to infinity of -3 over 3 to the nth power, which is the sum from 0 to infinity of -1 to the nth power, and that's going to be an oscillating situation, which is also going to diverge. So the interval of convergence here, IOC, we'll abbreviate that for, would be -3 to 3 with no endpoints included. And I guess I misspoke a little bit. I do actually need to find the derivative here in order to check the endpoints. But I know, because we're coming from the original function, I know from the theorem that r is still 3. I don't need to find that again. I do need to check the endpoints. So if f of x, which we no longer have on our screen, is the sum from 0 to infinity of x over 3 to the nth power, I can rewrite that in a more convenient differentiable form as 1/3 to the nth power times x to the n. And what that allows me to do is not have to use the chain rule here, because I can bring down the constant 1/3 to the nth power. I can bring down the n for each term, and I can subtract 1 from the power for each term. So I'm just differentiating it term by term. So I get the sum from 0 to infinity of n times 1/3 to the nth power times x to the n minus 1. So let's check our endpoints and see what we get. If x is equal to 3, I would have the sum from 0 to infinity of n times 1/3 to the nth power times 3 to the n minus 1. So I'm going to write that as the sum of n times 1 over 3 to the n, because we'll just bring that up. And then we'll make this one 3 to the n times 3 to the negative 1. Which gives me the sum of, let's see, these will cancel, and I'll have n over 3. And this isn't a case where we can use the nth term test, because the limit as n approaches infinity of n over 3 does not equal 0, so this diverges by the nth term test. All right, with the next one, x equals negative 3, we would have the sum from 0 to infinity of n times 1/3 to the nth power times negative 3 to the n minus 1. And we're going to do something very similar. The only thing that changes here is we'll have an extra negative 1 to the nth power. So this will be the sum from 0 to infinity of negative 1 to the nth power times n over 3. And this is another example of the limit as n approaches infinity of negative 1 to the nth power times n over 3. That's going to keep growing, but it's going to oscillate between being a really, really large positive number or a really, really large negative number. But it's not equal to 0, so this diverges by the nth term test. All right, so our interval of convergence for the derivative is also negative 3 to 3, not including the endpoints. Let's talk about the integral lastly. So I need to find, first of all, the integral of f of x, and I know that my original function f of x, since we haven't looked at it in a while, we had written that as 1/3 to the n times x to the nth power. So if we're finding the integral of this thing, the integral of f of x dx, that would be the integral of the sum of the integral, basically, of all of these terms. So that's going to be n equals 0 to infinity. We'll have 1/3 to the nth power, and then we'll have x to the n plus 1 over n plus 1 if you integrate the x to the n. So we know that our r is going to be 3. We just need to check the endpoints. So if x equals 3, the integral of f of x dx will be the sum from 0 to infinity of 1/3 to the n. We'll have 3 to the n plus 1 divided by n plus 1. So that will give me the sum from 0 to infinity of 1 over 3 to the nth. This will be 3 to the n times 3, and this will be n plus 1. So I can cancel here, and I get the sum from 0 to infinity of 3 over n plus 1. Now with this one, you do have to do a little bit of work on this one. There's options here. You can use possibly a direct comparison test, or one easy way to do this is to do what's called shifting the index. So to shift the index on this one, the only place it uses the index is n plus 1. So we know that the first terms here would be 3 over 1 plus 3 over 2 plus 3 over 3, so on and so forth. So if I were to start this with a 1 instead of a 0, in order to get that same series, I would want to have 3 over n, because then we'd start with 1 and have 3 over 1, 2, we'd have 3 over 2, so on and so forth. So this is what we call shifting the index. And this can be written as 3 times the sum from 1 to infinity of 1 over n, and this is a harmonic series, which we know is divergent. If I were to check x equals -3, I would have the integral of f of x dx being equal to the sum from 0 to infinity of 1 over 3 to the nth power times -3 to the n plus 1 power over n plus 1. And doing the same level of work that we did on the last one, we basically end up with the sum from 0 to infinity of -1 to the n plus 1 times 3 over n plus 1. And then if we just shift that index to be 1 to infinity, we would have -1 to the nth power, because we'd be starting at 1 instead of 0 plus 1, times 3 over n. And if you bring the 3 out, this is an alternating harmonic. So you can either do that or you can do the alternating series test. But this is an alternating harmonic, and it converges. So the interval of convergence for the integral is going to be -3 with a bracket and 3 with parentheses. So if we zoom out, we can see, just based on the work we've done, that with all 3 of these, they all have the same interval of convergence. The only difference is the endpoint. So the numbers are the same, but for the function, its derivative and its integral, the endpoints may change.